This video is for lesson 3-1. So we're starting into chapter 3 about the axiomatic system of geometry, which refers to all of the ideas of geometry being related to each other, new ideas being proved from previous ideas. Lesson 3-1 is about geometric definitions and two-column proofs. Our learning goals are to distinguish between undefined and defined terms, and to use properties to complete algebraic two-column proofs. So even though we're a geometry class, we're going to begin with some algebra proofs because you know more algebra than you do geometry. Geometry is an axiomatic system. That means that from a small basic set of agreed upon assumptions and premises, an entire structure of logic is devised. In geometry, it is necessary to agree on clear-cut meanings or definitions for words that are used in a technical manner. For a definition to be helpful, it must be expressed in words whose meanings are already known and understood. Compare the following definitions. The definition of the word fountain. A fountain is a rondelle that is bari, wavy, of 6 argent and azure. And then this definition of a guige. This is a belt that's worn over the right shoulder and used to support a shield. Which of the two definitions above is easier? Well, the definition of guige, because we understand the words used, a belt, shoulder, supporting a shield. This other definition, what in the world are these words talking about? So the idea there is that for a new vocabulary term to be helpful, it should be defined using words that have already been defined. The first definitions used in building a system, however, cannot be defined in terms of other vocabulary words because these are the first ones to be defined. In geometry, it's traditional to start with the simplest and most fundamental terms without trying to define them, and use these terms to define other terms and develop the system of geometry. These fundamental undefined terms are point, line, and plane. We don't have definitions for these three words, but we do have an understanding of what they are. Question 2, define each term using the undefined terms. So what is a ray? We can write a definition of ray using only words point, line, or plane. For example, a ray is part of a line bounded by one end point and extending in one direction. So this is a very short, clear way to describe what a ray is, and it uses the words line and point in it. Collinear points. What are collinear points? They are points that lie on the same line. Next, coplanar points are points that lie in the same plane. I want you to notice one other thing about defining geometry words. Every time it's a statement, and the statement always begins with the word that we're defining. That's the subject of every definition statement. After a term has been defined, it can be used to define other terms. For example, the word angle is defined as a figure formed by two rays with common endpoint. So once we had defined the word ray, we're now allowed to use the word ray in order to define the word angle. Question 3, define each term using already defined terms. Complementary angles are two angles whose measures sum to 90 degrees. Supplementary angles are two angles whose measures sum to 180. We can define these new words using the word angle because we had previously defined the word angle in terms of words we had defined. The process of deductive reasoning must have a starting point. A conclusion based on deduction cannot be made unless there's an established assertion to work from. To provide a starting point for the process of deduction, a number of assertions are accepted as true without proof. When you solve algebra equations, you are using deduction. You can use properties to support your reasoning without having to prove that the properties are true. Question 4. Using one operation or property per step, show how to solve this equation and name the operation or property used to justify each step. So we're going to solve this equation in the same way that you have done in your algebra classes. The only thing we're adding to it is we're going to provide justification for each step. Another word for step is each assertion, each statement that we make. So let's start by copying that equation down so that we can then do some work with it. When you write down the beginning or starting assertion, in this case that 4x plus 9 is equal to 18 minus 1/2 x, you're writing down the given information. So over here on the right side, I'm going to write given. This is given to us. Okay, next step, in an algebra class, we might solve this by adding 1/2 x to both sides. That creates 4.5 x plus 9 is equal to 18. But what is the property that says it's okay to add the same thing to both sides of an equation? That's called the addition property of equality. And so I'm going to write that here as my justification for why I've made this assertion. In your Algebra 1 class, you studied several properties or several things that are allowed to be done to transform equations. Next thing you might do to solve the equation is to subtract 9 from both sides. And that would create 4.5 x is equal to 9. But what's the justification for making this assertion that 4.5 x is equal to 9? Our justification is the subtraction property of equality. Finally, to isolate x, we can remove the coefficient of 4.5. We might do that by dividing both sides of the equation by 4.5. And 9 divided by 4.5 makes 2. So we've transformed this more complicated equation into an equivalent equation where the answer for x is explicit. We just know that the answer is 2. But what is our justification for dividing by 4.5? Why is that okay to do? And that's the division property of equality. You studied this in Algebra 1 class and learned that this statement says that you may divide both sides of an equation by the same real number. So here we have solved this equation just as you did in Algebra 1 and Algebra 2 class and provided reasons for each step. You can organize the steps and reasons used to justify the steps in 2 columns with statements on the left and reasons on the right. We just did that. This format is called a 2-column proof. Here's an example, a lot like the one that we worked out. So given this assertion that 3 times x plus 2 subtract 1 is equal to 5x plus 11. From this assertion, prove that x is equal to -3. So a step-by-step proof for this transformation process is to start by copying the given equation and then to start doing work on it. We might add 1 to both sides, creating this result. This was the addition property of equality that allows us to add 1 to both sides of an equation. Next, we might do the distributive property to create this result. And so our justification is the distributive property. Next, how about if we subtract 3x here and here to remove the x term from the left side and put it over here on the right? This is the subtraction property of equality. Next, we might subtract 12 from both sides, creating this result. So what's our justification for this? The subtraction property of equality. How about next, dividing by 2 on both sides to create this? What's our justification for this statement? The division property of equality. And finally, we can switch the right and left sides of the equation to put the variable to the left because of the symmetric property of equality. These properties are from Algebra 1 and Algebra 2 class, and they are reviewed for you on the side of this page of the geometry book. Okay, here's one for us to try, and this time we don't have the reasons. So supply the reasons used to justify the statement in the proof below. if we begin with this equation, can we prove that x equals 9? So what is your reason that you always put in a proof to start it off? We write the word given. Next, we want to figure out what has happened from the first step to create the result that's written in the second step. The only thing that looks any different to me is that there's been a 10 multiplied to what was on the left side and a 10 multiplied to what was on the right side. That's the multiplication property of equality. So you don't mind if I abbreviate that, do you, to make the video quicker? Okay, now let's tackle the third step. What is the justification for creating this result? Well, if we look at what we had before, it looks like that what's happened is the 10 has been multiplied to this group, and then when the 10 over 2 reduced, it created 5. We are substituting a 5 in place of the 10 over the 2. Same thing over here. When we multiply 10 by this, and notice how 10 and the denominator 5 reduced to a 2, we are substituting 2 in place of 10 over 5. This is called the substitution property of equality. Substitution is a real commonly used property from algebra class. We do that all the time. Okay, next step. How can we create this result from what came before? It looks like maybe some distributive property was done. Okay, the next step. How do we create this from what came before? Looks like we subtracted 2x from both sides. That's the subtraction property of equality. In the next step, the 15 was added over to create the 27. So that's the addition property of equality. To go from step 6 to step 7, we had to divide both sides by 3. And the thing that allows that is the division property of equality. So what we've done, if we solve the equation, probably in a very similar way than what you would do in an algebra class, but we've provided a justification each time. That's what makes this be a proof that the answer is x equals 9. Okay, next question. Complete the proof statement and write a 2-column proof for the equation given in item 4. Number each statement and corresponding reason. So if we start with this equation and we want to prove that something is true, kind of following the example we already did, does it make sense that we want to prove that x is equal to, and then whatever that number is that we get for an answer? Let's hold that thought and actually find this rest of this proof statement in the process of working out our proof. So we're going to create 2 columns. The first column will contain our algebra steps. The second column will contain the reasons for each step, and we're asked to number them. So step 1 is where you write down the given statement. In step 2, let's add the 1/2 x to the left side, creating 4½ x plus 9 is equal to 18. Our reasoning is the addition property. In the third step, let's subtract the 9 over to the right side. That creates 4½ x is equal to 9. That's the subtraction property. And step 4, if we divide by the coefficient, we get that x is equal to 2. This is the division property. Anyway, recall that we hadn't completely finished the proof statement earlier, and so we wanted to prove that x is equal to 2. And with these few steps of work, we were able to do so. Next, there are some check your understanding questions, and so I'll pause the video for you to work on these. So in this video, we discussed undefined terms and the idea that all of the rest of the words used in geometry are defined from those basic undefined terms. We also looked at using 2-column proofs to prove that our algebra solutions to equations actually work.